Hello, everyone. Today, I'm very excited to welcome Pandu to our USSM student chapter for a talk. I am Yinrong Xiao, and I will start with a quick introduction to Pan. Pan is a PhD candidate in aerospace and mechanical engineering at the University of Notre Dame, where he is advised by Professor Jianxun Wang. His research combines computational physics and AI. Now, Pan focuses on how these tools can push forward progress in biomedical and health science. And Pan is developing methods such as deep learning, generative AI, probabilistic inference, and differentiable solvers to work on problems such as medical image segmentation, patient-specific vascular modeling, and hemodynamic flow predictions. The purpose of his work is to build digital chains of the cardiovascular system that could help to improve diagnosis, risk assessment, and treatment planning for patients with complex vascular disease. Now the screen is yours. I will mute myself.
Thank you very much for the introduction. Hello, guys. I'm actually very honored to have this opportunity to introduce my talk on this HUG-VAS model. So the full name of this HUG-VAS model is called the Hierarchical NURBS-Based Generative Model for Vascular Geometry Synthesis and Controllable Editing. This work is led by me and my colleagues under Professor Jianxun Wang's guidance. My advisor, Jianxun Wang, has recently moved to Cornell University. And I will be kind of graduating after the end of this year. So the research I'm mainly focusing on is basically pushing the boundary for the next generation image-based computational fluid dynamics. So we're kind of using AI technologies to incorporate machine learning techniques to accelerate the process of characterizing the blood flow within human body to facilitate disease diagnosis, specifically cardiovascular disease. So this HUG-VAS model is kind of a very critical part of my work that can help us to accurately characterize patient-specific geometries, as well as use those geometries to conduct fluid simulation so that we can get more information about the flow field within the human cardiovascular system. All right. So to begin with, I would like to lightly introduce the background. So as I said before, the cardiovascular disease is the major focus of my work, which is a leading health concern. According to this report, it is saying that the cardiovascular disease actually even a major cause bigger than the cancer in terms of the death reasons worldwide. So it is very important so that we can leverage this image-based CFD pipeline to characterize the blood flow to assist the diagnosis of cardiovascular disease. So to briefly introduce this image-based CFD, it actually works in the following sequence. First of all, we acquire image scans from patients. It can be MRI or CT scans. The second step is that we extract the geometry from those CT scans. And this step is typically called the image segmentation. As you can see here is like a multi-arc tree structured vascular model that we can extract it out from the image scans. And later on, we can conduct CFD simulation on those geometries to obtain the blood flow within the geometry. And those information can be post-processed to obtain critical biomarkers and give it to the physicians or doctors for downstream diagnosis and treatment planning. The traditional pipeline of image-based CFD are mostly manual. They're kind of time-consuming, which kind of prevents their further adoption or application in clinical diagnosis. So our goal is to incorporate artificial intelligence mainly for the intermediate two steps. The first step would be the segmentation, where you extract the geometry more efficiently and more automatically. The second step is to accelerate the CFD modeling process. So why does this HUG-VAS model, sits? Where does this HUG-VAS model sits in this whole pipeline? Actually, in terms of the CFD modeling, we can actually do or calculate or predict the blood flow in two ways. The traditional way is just to use a first principle based CFD solvers, right? Currently, we are developing the next generation GPU-enabled differential FEM solver, which is kind of a, you can consider it as like a more efficient and differentiable enabled next generation solver to solve fluid dynamics. And it has the following advantages. First of all, it is fast. It uses auto differentiation to track the gradient. You can also use this gradient information for inverse problem like uncertainty quantification, for optimization problems, and it can be easily integrated with neural networks to create kind of a hybrid solver for more, inverse or design problems. So that's one part that we're doing on the simulation side. For the other side, you can actually use some deep learning surrogate models to predict the blood flow. We have previously published a paper that can predict the flow hemodynamics in single channel aorta, given the geometry of the aorta. And right now, we are using graph neural networks to extend from single channel to multiple channel using this multi-scale graph neural network model. So those are the works we are working right now. And in the future, we can actually, like I said, combine the CFD solver with some deep learning techniques to create kind of a hybrid model that can simultaneously have improved efficiency and also improved generalizability. However, if you want to compute the fluid accurately, you actually need a accurate simulation-ready geometry. The geometry needs to be very accurate for the flow to be accurate. And the second thing is that if you want to develop a data-driven flow surrogate model using neural networks, you're going to need a large cohort of geometry as your training data. And usually those kind of patient-specific geometries or patient-specific images are kind of sparse. It is very hard to obtain large size of data set for those kind of information. So basically, we need a good geometry characterization and also geometry generation tool first for us to finish this downstream simulation step, right? And that's exactly where this HUG-VAS model is doing right now. So I want to talk about the geometry characterization first. So the geometry characterization actually is called the image segmentation, are typically accomplished by either a manual approach or deep learning based automatic approach. The manual approach is basically using a software, while there's like an open source software like Vascular, where a user can open the image data in a software and build the geometry from scratch. It has several disadvantages. For example, it is mostly manual, meaning it is slow, and it is labor intensive, and you are inevitably introducing human artifacts during this manual segmentation process. There's also another approach, actually a very active research field in computer vision, is that you can actually create these auto segmentation models based on the 3D convolutional neural network architecture. So this is a previous work we have developed that can automatically finish this segmentation process given the patient image. However, those kind of models cannot generalize very well because it is actually data driven, and it also, because it is a data driven approach, the training label it is using is mostly coming from those manual segmentation process. So the trained model inevitably can inherit the artifacts containing in the training data, and also those kind of models can have surface irregularities, so that you need a lot of post-processing step for it to be ready to be used in a CFD process. So the question here is that how do we keep both the efficiency and also maintain a high surface quality from the segmentation? Another thing is about the uncertainty quantification. This is also a previous work done by me that kind of demonstrate, if you have uncertainty in your geometry, how much does this uncertainty propagate to the flow field? As you can see in the first row, if you have some kind of uncertainty induced by human artifacts, even visually you can see that those geometry kind of changes by a limited range, but the flow field can be very different if you're looking at the first row. However, for the second row, if you can quantify and reduce this kind of geometry uncertainty, you can see that the flow field can be very consistent. So here, another question is that can we actually incorporate some quantify or reduce uncertainty techniques in this segmentation process? So the answer is that we can propose a interactive semi-automatic segmentation, which basically the idea is that we will use some user input as kind of human supervised guidance, and we use the computer to do the rest of the things. So it's kind of a hybrid approach that is kind of half automatic and half manual. So for the second feature, it is called the geometry generation process. In this line of research, it is typically called as the statistical shape modeling, which is SSM for short. So this SSM workflow is typically done by two steps. The first step is to build correspondence between different patients. So if you look at the first figure on the left side, this is my previous work that kind of build a deformation process from the left to right. And the source geometry could be one patient, the target geometry could be another patient. And when we build this deformation from one patient to another, we kind of, parameterize the geometry into a fixed number of points, where the point is kind of corresponding between different patients. And there's also, future, more recent works that kind of extended into multi-branch. But those kind of point correspondence building process actually requires a lot of parameter tuning, and it's not actually performing very robust and well on this multi-branch topology. And also, there's later research that kind of build this correspondence not using deformation, but rather than directly parameterize the aorta surface. You can see those are different methods that can parameterize a surface. And once you use the same parameterization for different patients, the points are automatically corresponded. So the question here is that if we want to build this correspondence between patients, why not we just use NURBS? Because NURBS has been widely adopted in a lot of industrial applications. It is a very concise and neat way to represent geometries. And it is also compatible to a lot of downstream tasks, such as isogeometric analysis. So that's where the U letter comes from in our HUG-VAS model, which is representing the NURBS method, which can parameterize a 3D surface, represent the surface in 3D very well. All right, so the second step of this geometry generation is that once you build this point-to-point correspondence between different geometries, you can actually do some PCA analysis on the parameterized data set, and you can actually generate new geometries from this distribution of the PCA coefficients. So this is a previous work that is done in the single channel aorta, where they perform a PCA analysis on the point corresponded data set, and they can actually calculate the distribution of the PCA coefficients, and using a Gaussian fitting method, they can fit a distribution out of it. And during the generation, they just randomly sample from this Gaussian distribution and then combine with the PCA modes and reconstruct new geometries from the patient-specific ones. But for those kind of methods, they are linear methods because PCA is a linear method, which means that the geometry variation capability is kind of limited for those kind of approach. And also there's more, recent work that uses generative models, for example, diffusion models and general adversarial networks. But those kind of methods are more focusing on multi-branch artery structures rather than large size aorta vessels. And also most of the previous work focusing on very simple geometries, as you can see in this 2019 work. So for our approach, we are using a diffusion model to capture the intrinsic probability distribution of the geometry, because the training of the diffusion model is robust. And another very important feature is that the diffusion model can be cooperated with the Bayesian inference for conditional generation. And I will explain what is conditional generation in later slides. And this is where the G comes from, which is the generative architecture. And also the last letter H comes from a hierarchical setup. So in this method, we are actually encoding the aorta geometry in a hierarchical approach where we parameterize the radius and the center line separately using two independent diffusion models. I will introduce the detail later. So the HUG actually, consists the whole model, which is called the HUG-VAS. So let me formally introduce the design of our approach. So as you can see on the diagram, here we, on the left top corner, we actually first disassemble a aorta geometry into different branches. And then we use NURBS surface representation so that we can represent the center line using control points. We can represent the radial profile using those kind of different cross sections with radius in different directions, radial directions actually. And then we use a red model. You can see in the top, it's called the center line diffusion model, where we use this diffusion model. It's actually a classic DDPM model to capture the distribution of the center line. And then we, on the blue model, which is called the radius diffusion model, it takes in the center line as the guided information. So it is actually a classifier-free guided DDPM model that takes in the center line as the guidance, and it can actually generate this different radial the radius at different radial directions at different cross sections. And later on, you can combine the center line with the radius to reconstruct the NURBS surface, as you can see finally in the last row of this diagram. And later on, you can generate new branches for a new geometry for different branches. We actually use a Gaussian sampling method to determine how do we assemble those branches in different locations. And then we can actually assemble them into a multi-branch configuration. As you can see, is the synthetic model, and it will look different from the original model but preserving all the geometry characteristics of a patient-specific aorta configuration. All right, so the major highlights for this model is that we use the B-spline curve for the centerline NURBS, for centerline NURBS for the vessel surface. And we use the diffusion model for the control points. Here we use 16 control points to determine the tendency of the centerline. And then we use a image of 16 by 32. So the 16 represents all the cross-sectional locations string-wise, and the 32 represents the radial discretization at each cross-section. So as you can see in the red and blue images below the radial diffusion, each image actually represents this radial profile of a vessel surface. And lastly, we use this multivariate Gaussian sampling to assemble this vessel together to form a multi-branch architecture. All right, so after introducing the model, how do we use this HUG-VAS model? So the first way is to use it using the unconditional generation. So you can consider this unconditional generation is that if we have a original small size patient-specific data set, as I draw here, there's only 3 samples in the original data set, we can actually using this UG method to create a synthetic data set that has a significant larger size than the original one. And you can use this synthetic data set to do patient-specific CFD modeling. You can link it to biomarkers to do, prediction of the diagnosis. And you can do a lot of other downstream tasks. So this can be actually the exact same feature as the traditional SSM models. But there's another way to use this model. It's called the conditional generation. So for the conditional generation, if you look at the left side, you can see here is that besides those noise input into our HUG-VAS model, we can actually put in a extra information, and this information can be partial information from the whole image, and we can actually generate a new sample, but this time it is a new sample that is conforming to the conditional input we put in this model. Let me give you some example. So if you look at the middle figure on the second, on the bottom panel, you can see that we have 3 examples for this conditional generation. For the first one, you can see is that if you have a patient image, you can actually pick a point in this image, and we can use this point to generate different realizations of the diffusion sample, which is, in this case, different center lines. Those center lines can look different from each other. However, they all go through this conditional input, which is the green point. The second example is that you can actually select a contour from one horizontal slice from this image, and you can actually generate different surfaces going through the same contours. And similarly, you can also get a surface piece from a image data, and you can actually generate different surface samples that going through those green surface segments. And you can use this conditional generation feature to realize different versatile downstream tasks, which I will be introducing later. All right, so I will introduce the results in the sequence of unconditional generation and conditional generation. So this is the unconditional generation result. Basically, it is the denoising process for the diffusion model. The first row represents how the control point, represented by the blue points, how the center line, represented by the red curve, changes when you denoise the center line. And also the denoising process of the radial profile is illustrated in the second row in those red and blue images. And finally, if you put the center line and the radial profile together, you can actually obtain the surface, which, as you can see, it finally denoise into a very smooth, nice, new realization of different branches. And this is kind of a gallery showing that we can generate new samples that looks different from the original samples for different branches. But they are all preserving the characteristic of their respective branch. All right, and this is a diagram that kind of tells you how do we sample different locations to assemble the vessel together. As you can see, each bifurcation has like a ratio along the arc length that follows a multivariate distribution. So we kind of get this distribution from the original data set, and during generation, we just randomly sample from this multivariate Gaussian so that we can get new bifurcation points, and we use those new bifurcation points to assemble the branches together. And the assemble process is simply by using this Boolean operation and seamlessly connecting two branches together. And this is the full gallery of the newly generated multi-branch geometries versus the original gallery. This is some statistics showing how realistic our newly generated geometries are. We actually pick 9 classic geometric biomarkers that kind of calculate the distribution of those biomarkers for the original data set, which is the red column. The PCA Gaussian approach, which is a state-of-art approach, which is basically doing PCA corresponding mesh and fitted multivariate Gaussian distribution. And the green column is actually leveraging the hierarchical architecture of our model. So as I previously mentioned before, we have a hierarchical representation for the center line and the radius, right? So you can actually fit 2 different Gaussian distributions for the center line and radius and sample them in a decoupled way, which gives you the green column. And finally, the purple column is our model. As you can see, our model, which is the purple distribution, are actually the closest to the original distribution, right? And generally speaking, the PCA-based approaches, which is the blue and green, are kind of significantly higher, variety than our diffusion model. I will later show you some failed examples on PCA-based methods, because those PCA-based methods, even though they have higher variation range in terms of those biomarker distribution, they can sometimes frequently result in bad samples that some of them are very similar to the original data set. Some of them are totally unusable in CFD simulations. All right, so this is a latent distribution of the samples. You can see the red points is original. The triangles are PCA Gaussian. The green triangle are PCA Gaussian decoupled. And the star purple is the diffusion model. This is saying, again, the PCA-based methods has larger distribution than diffusion, but our diffusion model captured similar distribution as the red points. And this is actually calculating the distance from the newly generated points to the linear space spanned by the training samples. As you can see that the PCA-based method has higher residues in decoupled. For the PCA Gaussian without decoupled, the new generated points are always going to be lining in the linear space spanned by the training points. So all the residue is going to be 0. For the diffusion model, it is not 0, but for the decoupled Gaussian sampling method, it has the largest residue or distance from the original linear space. However, the PCA Gaussian decoupled method will result in a lot of failed cases. All right, so this is the failed cases I was talking about. As you can see on the left side, we even compare it to a previous CV method. It's called point voxel diffusion. The point voxel diffusion just generate new samples that are not physical at all. It fails at generating plausible branches. For the PCA Gaussian method, you can see that on the first red box, those samples are very similar to the original training samples. The second box is the surfaces that is not usable at all because it has surface irregularities. And for the PCA Gaussian decoupled, you can actually generate some plausible new geometries. However, for the second box, you can see that it also results in a lot of unusable cases. And this is just showing that we can actually use this simulation-ready meshes to conduct CFD simulation, we have different simulation for different samples. And this is an animation of the streamline for our transient simulation. All right. So after those discussion about unconditional generation, I would like to introduce more about our conditional generation. We actually have multiple different utilization of this conditional generation feature. And this is the first one. It's called the generating center lines from the point prompts. So let me introduce you the idea of this pipeline. If you look at the raw image, this is a patient-specific image, you can actually obtain the center line in two ways. You can go the slow way, which is the left bottom corner, using vascular approach. It's going to be very slow. However, you can use a faster way. So the fast way you do it is that instead of clicking every point along the center line, you only have to click it 5 times. So those 5 times are very sparse, and the 5 is very small compared if you want to use vascular to create the center line, you're probably going to click more than 20 points typically. So only using those 5 green points, and if you put those 5-point input in the HUG-VAS model, it can actually generate the center line for you, which is much faster than clicking over 20 points using the traditional approach. And this is showing the difference between the unconditional and conditional generation results. If you use the unconditional generation, this is basically saying that I just want to get new realization of the center line, right? So as you can see, those red curves are different samples, and I have an ensemble of those generated center line in the rightmost column, and the black line is the ground truth center line from the patient-specific model. And if you use this 5 user point prompt, and you can actually generate the new samples that are different from each other, but it actually goes through those 5 points. As you can see, those 5 points are, the information is sufficient enough so that the variety or uncertainty in those ensemble of new realizations are kind of small enough, and they kind of converge to the ground truth center line. All right, so this is a sensitivity study basically saying that if I give HUG-VAS 2-point prompt, 3-point prompt, all the way to 5-point prompt, and I'm computing the ensemble of those realizations. As you can see from left to right, the ensemble uncertainty is kind of reducing, right? In the case of 5-point prompt, the uncertainty kind of collapsed and converges to the ground truth. And this is a statistical plot just quantitatively showing that this arrow bar, which is equivalent to the variance of this ensemble, is kind of decreasing if we increase the prompt point. And the second conditional generation user case is simply generating the surface from contours. So if you have a raw image again, typically if you use vascular, you have to go through the cross-section along the center line, probably even like by 10 contours or 15 contours. But in our case, all you needed to do is just to select 4 horizontal contours and put it into the HUG-VAS model. The HUG-VAS model will use the contours to generate an intact surface for you and align to the ground truth. And this is a result for the unconditional and conditional generation. As you can see, for unconditional generation, it can generate a variety of new samples. But if you give 0.3, in this case, 4 contours to the HUG-VAS model using conditional generation, it can actually generate different surfaces that are slightly different from each other, but they all kind of converge to the ground truth surface, which is the purple surface here. And we have the similar plots for the sensitivity study. You can also see that the uncertainty of the surface this time kind of reduces if we increase the contour plot. And we have both the visualization and quantitative proof to support that. All right. So this is the third application for the conditional generation, where this is a patient where if you have a patient-specific data, and usually this patient-specific data can have different signal-to-noise ratio in different regions, right? Or even some of the image data can be missing or damaged. So imagine if you only have this small proportion in your patient image that has high quality, you can actually do some segmentation in this small high quality region to get a high quality green surface segment. And we can use this segment, put it into the HUG-VAS model, and we can generate an ensemble of different surfaces that are, showing classic aorta geometric features, but they're different from each other and all align with the surface segment. And this can be considered as like a recovery of the full geometry from partial data. And for the fourth application, this is actually relevant to low resolution CT scans. For this scan, interestingly, we are actually taking a scan of a rabbit. For the rabbit, the aorta is much smaller. So if you don't change the resolution of your CT image is going to be very coarse. As you can see on the left side, this CT resolution is very low on the Z direction, right? So if you use a segmentation model to obtain this voxel prior, which is the the voxel composed cluster of a geometry. Imagine you have to construct a smooth surface from this highly not smooth voxel prior. You're going to have a very hard time to smooth out all those step features, right? But if you have the HUG-VAS model, you can just simply sample some points from this surface and put it into the HUG-VAS model, and the HUG-VAS model can automatically generate this smooth surface for you. And the fifth application is what we can use the HUG-VAS model to do surgical implant device shape optimization. So this idea is that if you look at the first row, if you have some image scans, you can actually manually segment the healthy part of this patient. Actually, this patient have a geometry in the left bottom corner, which have an aneurysm in the descending aorta region. So if you only take out the healthy part of this patient, you can actually put this into the HUG-VAS model, and the HUG-VAS model can generate an ensemble of the aorta geometries and have different size of the aneurysm for different realizations. And those different realizations kind of construct a realistic prior geometric space. And you can actually find the optimal geometry within this space. So the process is that you can first parameterize the geometry, especially the diseased part, using a small number of center line and the radius. And those center line and radius can construct the surface, and the surface can be put into a differentiable or surrogate model solver, differentiable solver or surrogate model to compute the flow field. And you can specify some loss function for the flow field, and it can back propagate the gradient using auto differentiation, and to optimize the center line and the radius values such that we can find the optimal shape within this realistic prior geometric space. And this is some results where we use not a differentiable solver, because that differentiable solver we are still in development, but we train a CNN surrogate model that directly maps from this centerline and radius values to the downstream flow field. And we use the following, loss functions to prevent abnormally low and high wall shear stress. And we perform this optimization to get the optimal shape that has the healthiest blood flow. And as you can see here, this is the optimization result. From left to right is the optimization process. As you can see here, the geometry kind of use this image to represent the radial profile for the diseased surface. And this masked area is where the white regions are basically the abnormally high or low surface areas. We're kind of minimizing that during this optimization process. And we have this wall shear stress and pressure distribution during the optimization process, where the distribution kind of the distribution of the wall shear stress and pressure kind of optimized to a very good state. And on the right panels are the optimization process in a 3D view, where you can see that the aneurysm kind of gradually reduce, and finally giving us a very healthy aorta. All right. Another application that is very important in our pipeline is called the semi-automatic segmentation process. So when we propose this segmentation process, this is what we are thinking. In this figure, I plot out the traditional segmentation process, right? Where giving the image data set, you need to go through all those manual steps to create the points, the center line, the contours, and finally construct the surface. Now, but our idea about this semi-automatic segmentation pipeline is that if you have the, if you have this patient image, right? All you have to do is to first select one contour. For example, in here, I label it out using a dashed orange line. And you use this orange contour, put it in the HUG-VAS model. It can actually generate an ensemble of different aortas represented by those gray transparent surfaces. And the user can actually observe the change range or the variance at different locations of the aorta for this ensemble. And for example, the next contour can be selected at this end of the arch location. And we use this second contour, put it into the HUG-VAS model. You can see that the ensemble kind of uncertainty of the ensemble kind of diminished, right? And we still have a bit of large variation at the end of the aorta. So we select that location, segment a 2D contour out of it, and we put it into the HUG-VAS model. And finally, we also still have a little bit of variance at the tip of the end of the aorta. And we use the fourth contour to reduce the uncertainty at that location. And finally, you can see that all the uncertainty collapses and converges to the ground truth aorta, which exactly serves the purpose of the segmentation. And we actually did a software demo where I can show you the process of it. We actually built a operable 3D plus 2D viewer, just like the Vascular. And the first step is that we can select one contour in this left top section and push a button, and you can actually get the first ensemble, as you can see in the right bottom corner. And then we use the second location for the second contour. and we put it into a HUG-VAS model again. And as you can see, it will generate a symbol that has a reduced uncertainty. And then we move the horizontal slice downstream a little bit to further reduce the variance over there. And after this process, you can see that the newer ensemble should have less uncertainty over there. And finally, we move it to the end of the descending aorta, and we put into the HUG-VAS model again. And finally, you will get a very nice converged solution. That is basically the final segmentation result. All right, so here is a comparison between the conventional vascular contour and the HUG-VAS model. We kind of fast forward the process, and finally you can see that our model, which is the HUG-VAS automatic segmentation process, only cost us like 4 minutes, but for the vascular, it costs nearly 20 minutes, which resulting in a 4 times speed up. Note that there's new technologies that can accelerate this diffusion denoising process. So we can potentially make more improvements in the denoising process to make it even more efficient, which can potentially lead to even more speed up for this segmentation process. All right, so here are the conclusions. This is basically saying that our HUG-VAS model can synthesize geometry. We can perform semi-automated segmentation. We can use that in the downstream CFD solvers, and we can integrate it into differentiable pipelines to do inverse problems, just like the implant shape optimization process I showed before. And in the future work, we will continue to do on the FOM solver. We will do something on the the GN surrogate model as well. And we can actually incorporate this differentiable FOM solver with the HUG-VAS model to do the optimization process with higher accuracy. All right, thank you very much. I have all the relevant papers as barcode over this page. Feel free to scan it if you are interested. And I'm happy to take any questions. Thank you.
Thank you so much for your great research introductions, and it's very clear. And also it seems like a great work that can help to create the database of the vascular vessels. Does anyone has any questions? Well, I do have one question. So in your simulations, you think you don't take account of the section shape and make it to be the same and only use the radius of the sections?
Use the radius of the section? Can you explain more?
So from my understandings, you has 2 parts to describe the shape of the vessels. One part is the center lines, and the other part is the different radius at the different sections.
Exactly, yeah.
So you think like the section is the circles.
Yes.
I see.
So if you look at this radius image, right?
Yes.
In here, every row is actually representing the radius of this one. This one.
Yes.
We actually have 32 radius in different radial directions. And if you look at this animation, you can see that during the denoising process, originally it's kind of noisy, which resulting in a very ugly shape you can see over here. But after the denoising process, you see it actually converges into a very smoother field where the blue values actually representing smaller radiuses, the red region representing the larger radiuses, right? So if you look at the denoising process of the surface, you can see that the final shape kind of consistent with this radial profile, where the downstream regions are kind of having a smaller radius, right? Where this one has kind of a small like a not small aneurysm, kind of a diseased aneurysm here where it has abnormally large radius, which is corresponding to the red regions in this finely denoised radius image.
I see. And I also think it is very clever to using the diffusion models to deal with the low CT image with a lot of noises inside.
Yes, yes. So I think if you, I can show you some more insights on that. So actually, let's see. So if you look at this result, so this is called the point voxel diffusion, which is a classic, computer vision technology to generate 3D shapes, right?
Yes.
And as you can see here is that because it is directly taking all the point clouds as the training data set, as the training sample, right? So first of all, the sample for the generative model has a very high degree of freedom, right? So if you have some noise in your training data set, you can see that the generated quality is pretty bad because let's say in a denoising process, it's not very ideal. You will end up with a lot of, surface vacancies or, very bad qualities simply because you cannot handle this noise. But what we are adopting is a NURBS plus diffusion approach. So first of all, the NURBS kind of significantly reduce the degree of freedom, right? So if you use like a mesh representation, you probably need thousands of points to represent this surface. But for this NURBS representation, you only need 16 for the center line. You only need like 16 by 32 for the radius, which is a significantly smaller sample size. And if we use diffusion model, first of all, diffusion model is very robust. Even if you have some kind of noise in your training set, you will probably get away with it with some fine tuning because that's just why everybody loves diffusion model. And also imagine if you have some kind of denoising, not ideal behavior, you have some points that kind of still have some noise, physical noise inside it. But if you pass it through the NURBS, NURBS surface construction algorithm, you will still get a smooth surface, right? Because the noise is just the control point. When you interpolate the control points, it's still going to be very smooth. But if you don't use NURBS, like use this PVD algorithm, you will very likely to have this surface that is completely not usable in downstream safety tasks. Yeah.
How do you decide the 64 units rather than using more or less like 128?
Yeah, that's a very good question. So first of all, there's like two different discretization, right? The first one is how do you discretize this center line, right? Along this center line, like this. So for this center line, how many cross sections should you have? For this radial direction, how many radius do you have? So for the first one, if you are very familiar with the Vascular software, when you construct the cross section, if you put two less cross section, you cannot construct this shape. You will probably skip it. You will only have like a polygon shape of the center line. Which kind of lose the fidelity of the center line shape if you use two less cross sections, right? But if you use too much, for example, you use like 30 or 40 cross sections along the center line, those cross sections, like I draw here for the blue cross sections, will intersect. So when those two cross sections intersect, the surface is not usable. So you have to pick the sweet spot for this aorta. So we actually have different discretization for different branches. Currently, we have 16 for the main, 16 for here. This is a LSA, LCCA, RCCA, but for the RSA here, we only use 8, so half of that. So for different branches, you have to pick. the sweet spot for the discretization on the streamline direction. For the discretization for the radial direction, it also depends on what kind of surface you choose. For this aorta in particular, because aorta is kind of the largest vessel surface in our human body system, right? So there has a lot of surface features that are probably having effect on the CFD computation on the final flow field. So you still have to have enough angle discretization so that it can represent all the surface curvature change along this radial direction. And also, but if you use it too much, the NURBS itself will create very, if your diffusion model is not trained very well, it will create those wrinkles, which is unphysical. So you also have to pick the sweet spot for the angle discretization in the cross section. So currently, after we test with different numbers, we select 32 for the aorta. But if you wanted to parameterize like smaller vascular system, for example, the cerebral, the pulmonary artery, or the coronary artery, you probably don't need those 32 discretization. You probably want to pick less, like 16 or 8.
I see. That's very interesting. And I just have another questions because I'm not quite familiar with these vessel structures. I was just thinking when we generate new vessel structures, why don't we directly using something like the Monte Carlo random walkings to change different parameters a little bit and regenerate those central lines and change some radius a little bit randomly, but we need to use your HUG-VAS models.
Yeah, so I think first of all, if you use Monte Carlo method, it's slow, right?
Yes.
Because well, the Monte Carlo method is also have to have like not some kind of knowledge of the distribution, right?
Yes.
So for diffusion model, I think the first important thing about diffusion model is that it can incorporate with DPS. DPS means DPS means diffusion posterior sampling, where you can do conditional generation, right?
Right.
You can do some, construct centerline from points, surface from contours. Those are kind of the core technology that realize this auto segmentation process. So that's the first point. The second point is that the current state of art generative technologies kind of have different approaches, various different approaches actually, to accelerate this denoising process. I think it's a more active field where people proposing a lot of ideas to accelerate the denoising diffusion process rather than the Monte Carlo process. For example, you can actually learn a ODE surrogate for your denoising process. And using that, you just run the ODE surrogate to do this denoising, rather than right now I'm using a so-called Lagevin process, which is a stochastic process, meaning that you have to do the denoise and also generate a random noise to make it stochastic, because that's just how the default diffusion denoising process works. But there is a lot of techniques like those ODE surrogates to accelerate this process. So potentially, it will have higher efficiency compared to just using a Monte Carlo method.
I see, that makes sense. And how long does it take to run a patient-specific CFD models if I directly using the fruit CFD method instead of machine learning?
Yeah, you're talking about the downstream CFD simulation, right?
Yes.
Right. So for that one, the bio community typically use like FEBio, Abacus, and also I think Vascular has its own multi-physics solver right now. So typically when you do that, for a static case, it will probably run hours if you have like higher resolution. For a FSI, for a transient case or even FSI case, it can run for days or weeks. That's the typical number right now. But we have, so like I said, we are actually developing surrogate models for this. And we also develop like differentiable solvers on this. For the surrogate model, it is data-driven. Once you train it, the inference speed is very quick, right? It can give you the solution in seconds or minutes. But for the differentiable solver, we are testing right now. We are expecting around more than 5 times of speed up using this new architecture that kind of leverage the modern, hardware device like, graphical computing units versus, traditional solvers, Fortran-based solvers, C++-based solvers. They're typically using CPU to run the simulation cases, right? So both the surrogate model and the differentiable solver, or potentially in the future hybrid models, will have significant speed up for these downstream simulation. Yeah.
Yes, that really helps for the future clinical applications.
Yes, I agree.
Yeah. Thank you. And we also have some general questions like, what do you think is the key challenges in the digital training models from research to the clinical practice?
Yeah, I think the biggest challenge right now lies in 2 points. I'm picking up the most important point. The first point is the efficiency. I think the efficiency is a very important point because in a lot of cases, actually right now, if you ask a doctor about how you're going to deal with a patient when you know some of his information or some kind of scan comes in, right? Usually when doctors do the decision, they would prefer a very fast feedback. The patients would prefer the very fast feedback. So the doctors will mainly rely on his years of experience of previous cases of different patients, right? So they will typically look at the X-ray scan or CT scans, and they do some, judgment. For example, what kind of, catheter, those kind of implants, stents that we can use catheter to put in the diseased region of the vessels to resolve the blockage of the vessel. Those kind of cases, they will basically using their experience to make the decision in one afternoon, and they will even perform the surgery next day. So this timely feedback is very important. But if you use the traditional image-based CFD to create this digital twin, right? It will cost, like I said, weeks or days of the simulation. That is too slow. So basically, the timely feedback requirement is not met, which means which will lead to like the clinical diagnosis basically do not adopt this CFD results. That's the first part. The second part is about the uncertainty. So right now, typically, if you do any simulation, especially vascular simulation or FEBAM simulation, whatever software you use, you typically just give the doctors a unique field or a single field, right? It is a field where it has a lot of ideal assumptions. For example, the blood has a non-Newtonian assumption. Sometimes the blood has turbulence, whereas your solver probably didn't resolve the turbulence at all. There's also parameters you use in your simulation. The resistance parameters can be inaccurate. Those kind of assumptions are all reflected in your CFD results, which means your CFD results are highly likely not very accurate compared to the realistic cases. So those kind of trustworthy, the level of credibility or reliability is a major challenge that is preventing the CFD results to be used in clinical diagnosis, which brings us a need for uncertainty quantification. So if you can actually quantify this uncertainty, and by the way, this uncertainty can be coming from the image. So if you have a patient-specific image, the image itself contains uncertainty because the sensor can be noisy, right, when you do the scan. And when you do the segmentation, there's uncertainty from the human artifacts. When you do the simulation, the CFD model has uncertainty. So this uncertainty can actually propagate throughout the whole pipeline. And if you can quantify this uncertainty in your final propagated CFD results and give it to the doctor. So this time you're saying that, okay, I can show you what is the most highly likely mean flow looks like. I can also show you there's like have a range of outcomes that you can trust. Of course, further from the mean is less trustworthy. Closer to the mean is trust. You're kind of preventing more, giving more information for the doctors to make decisions. So that's also a very important point to realize, to push the edges of this clinical adoption of digital twins.
Yes, thank you. And I do think that your works with the interdisciplines include the AI's fluid mechanics and statistical analysis with analysis advance these areas. And so you're going to graduate soon. How do you think about your graduate life at the University of Notre Dame? And what do you think to make it unique?
Yeah, actually, yeah, so I've been in Notre Dame since 2020. I think Notre Dame graduate life is pretty good. So first of all, I think Notre Dame provides a very versatile cultural environment for the students. I think there's like kind of different, activities after work. You can actually make a lot of friends, and people are very friendly. I made a lot of friends during my time here. So I think first of all, it's a very versatile graduate life. Plus, there's occasionally some football games. I think we have a very big stadium where we compete with other university teams in football. So I think for life wise, I think it's a very awesome place. And in terms of the research life, I think for the Notre Dame department, there's a very large group of professors or PIs focusing on biomedical research. And also for my advisor, and he has also some collaborators within the University of Notre Dame, they are actually doing more kind of fluid problems, right? So there's kind of one branch of research direction doing physics problems. I think in our group, we also not only restrict to turbulence or fluid dynamics, we also do other physics simulations like modeling heat transfer in chips, those kind of other physical problems, or like general PDE problems. So there's one line for research of that. And also there's other line of research doing biomedical research, which is more inclined to biomechanics, which the biofluid is kind of one small aspect of that direction. So you have like versatile research direction going on in the same department, which creates an awesome opportunity for people like me doing interdisciplinary research, to learn from those very knowledgeable PIs, to talk with them, to brainstorm ideas and create this new collaborations. I actually right now have multiple collaborations with PIs and students in both sides. So yeah, so in general, to summarize, I think my graduate life, graduate personal life, graduate research life in Notre Dame is very good. I really enjoy my time here, and I think in the future it will help me to go further in this interdisciplinary direction, and hopefully I can use all my expertise I learned here and contribute more to this interdisciplinary direction, combining biomechanics and fluid mechanics and AI research.
Yes, that sounds like to be a great atmosphere set there between those PIs with a lot of
Yeah.
in-depth collaborations.
Yes,
And
yes.
now you feel you looks like a very successful researchers and has
Thank
a
you.
in-depth understanding of your areas. So from your point of the views, how do you think if a PhD student is ready to graduate?
You mean when does the PhD student is ready to graduate?
Yes,
Oh,
how
I
can
see.
you tell if a PhD student is truly ready to graduate?
I see. I see. I think the most important quality for a PhD student is that you have to form your own way of independent thinking. I think the basic skills are one aspect, but the idea proposal is another aspect that is even more important. So I think you have to, yeah, so to briefly speaking, you have to have both of those two aspects to a certain level to be ready to graduate. So the basic skills is like, how do you conduct experiments? Well, in my research, you have to be good at, you know, downloading GitHub code, reading them, playing with them, run your own results, reasoning with them. So those kind of basic skills. And I'm pretty sure in other graduate students who do experiments or even in other type of PhD program, they have to be mastering the skills that is very basic in their research field. So that's one thing. But I think the more important thing is that you have to have your own way of thinking. I think the most important thing is that you have to have a very efficient and effective approach to first look at a research area right now, which is active, where a lot of people are proposing new ideas and pushing out new models. You have to have your own way of overview the field. You have to know their work. How does their model, sits in the current spectrum of all the SOTA methods, and then you have to identify the need or kind of the limitation of the current work, and you have to have your own way of proposing new ideas. And when you have an idea, you can leverage all the skills you mastered before to execute your research. So I think that's the most important qualities that a PhD should obtain. And if you are kind of familiar with this process and you can successfully implement this process using one paper or two paper, something like that, I think you will be ready to graduate. Whether you are going to the industry, whether you're going to academia, those skills are going to help you very very effectively in the industry or in the research trajectories in your future career. Yeah.
Thank you. That is really helpful. I agree. It is important to build your own research frameworks and have a better understanding of your research areas.
Yeah, I
And
totally agree.
yes, and if you don't mind, we will upload these videos recording to our YouTube channels. And also, please send me your address. We will prepare a gift for you. I will
Oh,
tell you my phone number through the email
yeah,
later. Thank you. It
sure.
is
Thank you
very
so much.
helpful. Yeah.
Mm-hmm.
Yes,
And
it's
yeah,
very great.
I also
Yeah.
want to show my gratitude for your invitation. And I'm deeply honored to present my work on this seminar series.
Yeah, the great thing is that we will keep your videos so many people who is not attending, they can still have access to
Oh, yeah,
understand this
perfect.
field of this cutting-edge research. It's really impressive. Thank you, and wish you
Thank you
all
very
the
much.
best in the future. Bye.
Thank you. Bye-bye.